I'd like to thank organizers to let me have this additional talk. I was not scheduled, but I thought that Richard deserves. He really changed my life, and in 15 minutes you will see why PPC and especially Richard did so much to my life. Okay. I basically, in 1976, I got married, and my father-in-law in Poland gave me a very generous gift. It was HP 25. At that time, you could buy them in Poland only for dollars. Local currency was not exchangeable, so you had to order it from Vienna. It took about half a year after you pay. And the price was, I still remember, $140, which in US was not much, but in Poland it was roughly my yearly salary. That was, exchange rate was so stupid at the time.
Did it use Polish notation?
Yes. In fact, when I got this calculator, I protested to HP that all the literature contained wrong data. They were claiming that RPN was invented in 50s. This is not true. I have an original paper by Jan Łukasiewicz, who invented notation. It was, of course, not called Polish. He called it notation. He was logician. And he published first papers in 1920s. It became known to the West when he, after the Second World War, he emigrated to Ireland and he started publishing in English. Basically, he was the inventor of so-called fuzzy logic. So many of you who use the multiple valued logic probably know his name. And the only reason the notation was called reverse Polish was because nobody could pronounce his last name. Łukasiewicz, and in fact in Donald Knuth, the book about algorithms, Knuth had to add the letter L/ to properly spell his last name. So, well, but you can check, in tech, he added the letter L/ just to write this single name. Anyhow, together with the calculator, I started receiving the literature from HP, those, whatever it was called, keynotes or something, and that's how I learned about PPC. And in 1978, I decided to join. I got fairly low number, 2865. I sent few contributions, typewritten on very poor typewriters, so they were always retyped by Richard. And it just happened that in 1981, I got a job in Texas in the oil prospecting company, which today it's part of Halliburton Oil Services. And I was, as you can see on the photos, I was programming larger HP computers, but knowing how HP worked was very helpful. I was taking 85 home. The photo shows Rubik Cube, Ball's Liquor, and the book about Beatles. So it's a very well dated from mid-81. As soon as I came to Texas, I ordered 41C, and it was a time when PPC Club started the PPC ROM project. So I signed, I got, Jake Schwartz told me which number I got. It was 417 ROM. Few years later, when I returned to Poland, I sold the whole system to a friend of mine who was a big fan, because I moved to, basically I started using Macintoshes. I will tell it in a moment. But recently I started collecting 41Cs, and I bought a PPC ROM number 5150. I even know who was the owner. Jake found it on the list. It's engraved with the number. So programming 41C was a big fun. I mean, for 21, everybody knows 49 steps. It's not much fun. But 41C was a big thing. In '82, I had to return to Poland because they declared martial law, and my family, my wife, my kids were there. So I was finishing my PhD thesis, partially programming it at 41C. I submitted few programs to the European Users Library, and they were giving so-called overlays. If you submitted 3 programs, you were getting so-called bronze overlay, which is kind of a neat thing. I still have it. It's slightly broken.
Want to sell it?
Well, if you want, yes. If you are collecting, I mean, I am not that much into the memorabilia.
Only $5 for the book. Maybe we can work something.
Okay, sure. I can send it to you.
Don't sell yourself cheap.
No. It's I did it for fun. Most of my programs were really not scientific. It was like astrophotography correction for the time length of exposure and things like that. Very niche programs. The only one which really I am proud of is the program to convert any units to System International or the basic units used in physics. The program was written that way that you can extend it by adding any units, imperial, you name it. And you can find it in the volume 12 in number 2. It's a fairly long program, but Richard was kind enough to convert it into barcodes. I had barcode reader, but I didn't have a printer. But in this catalog of programs, it is included. In 1986, effectively, I stopped using 41C because I got my Mac. This is another story how I overcome the so-called COCOM restrictions. Macintoshes, they were built on Motorola 68000, and those processors were using Titan missiles. And some idiot put it on the export restrictions, although you could buy processor in every Radio Shack, So it's a long story. Anyhow, I got my Macintosh in '86, and I started programming this in Fortran and other stuff. Now, I noticed that in PPC Journal, there were plenty of stories about random number generators. For some reason, people were, at that time, we are talking late 70s, early 80s, people were programming random number generators. And it just happened that one of the first programs which I wrote professional as a physicist was for Monte Carlo simulation, which of course used random number generators. I was programming at the time on the CDC 73 mainframe, and of course there was a ready random number generator. I was so naive that I used a code from Oak Ridge, and I sent them my code. I didn't realize that Oak Ridge is the place, or nearby here, where they built atomic bombs. So my program is still in the library. Now it is, after September 11, it is only as an abstract. But I now, as a US citizen, I can go there. But at that time, I couldn't enter the laboratory, which had my own program. There is a reference where you can find it. And I wrote a few more programs using Monte Carlo methods. In 1983, I defended my PhD thesis, which was basically about calculating radiation damages in semiconductors, mostly proton, but also other ions, I used all the time those programmable random number generators. This morning, it was very funny. When I was introducing myself, Namir, who was sitting by me, said, "Oh, so you published this paper in PPC about Monte Carlo integration?" And I found it. It's true. It was in 1980, but that he, after 44 years, he remembers. I don't know how it's possible.
PPC, that stands for constant memory.
Well, you have a very good memory, Namir. Yes, so this was a kind of a contribution which I was making. I think perhaps very atypical. The one which I am proud of, which PPC allowed me to publish something which was very hard to get published otherwise, was visual testing of various random number generators. At that time, I had a Sinclair Spectrum, which had a color monitor, and you can address directly the video memory. So you can basically dump a series of random numbers on the screen, and then I photographed. Unfortunately, PPC Journal was only monochromatic, but you can still see the huge difference. Some generators are very good, but some are very bad. You know, there is an obvious pattern, and this is a visual method of testing random number generators, which nowadays, as I will show you, is also very helpful. So this was probably one of my last contributions to PPC, because after that I really started using Macintosh and stopped programming 41C. Fast forward to 2024. In '96, I moved to USA following my wife, who got a postdoc in Boston. In 2008, after some complications, I got US citizenship. I worked at MIT and UCSD. Recently, I founded a startup which makes instrument-to-size nanoparticles. It was sold to a Japanese company, and during pandemic, basically being retired, I decided to start a company with a name Randimon, which really means random daemon. Daemon like in Unix process. And with 4 friends, we called it Old Fart Startup, because the average age is over 70, 4 of us. And we were very successful. We built several prototypes of random number generators, physical random number generators, based on tritium and nickel-63. We already got 11 US patents. Somehow, there is a fast track in US PTO if you are over 65. My partners, they are joking that they have to do it fast because otherwise the inventor will die. So we got 11 patents, which for 4 years old company, I think is a very good result. And some of the patents I will show in a moment were using also Monte Carlo simulations. We call it true quantum random number generators, because they are based on quantum entropy, beta decay, which is independent on anything practically around. So, and of course, the generators were tested. There are batteries of tests. The only problem is with random number generators is that you can prove that the generator is perfect if you test infinite number of bits, but that will take forever. So practically, you always have a limited time. So you have only statistically, you can say it's at the 99% probability or so. In 80s, I didn't knew that. But in early 50s, John von Neumann, the famous mathematician, wrote about the sin of those who are trying to generate random numbers by using arithmetical functions. And this is still valid, and this is a good example of how the wisdom of a good mathematician got forgotten. I'm saying that it was forgotten because, for example, if you start doing simulation in Visual Basic in Excel, and you need to simulate plenty of points, it turns out that the standard random function in Visual Basic has only 20 million different numbers. So if you generate like billion of points, you don't get better results. And initially I didn't understand it. You know, we were running more and more, and they were still very jaggy.
We call that the cycle length of the...
Yes, the period of the period of the generator. There are, of course.
Besides the period, many generators also have a tail.
Yes, but in this case it is just.
They have an initial sequence that doesn't get repeated before you go back into the.
Well, in this case, it's just 20 million numbers. You can, of course, program something better with 10 to 12 period.
The random number generator, well, I forgot what that is, 50,000 or something other than that?
Well, it depends. I was showing the tests of various, which you published.
I'm sorry.
Again, thank you. Some of them are really very bad. I mean, the sequence is really very short. In this case, we are simulating nearly 10 to 10 electrons because very few reach the matrix. Why random numbers are important, especially in modern cybersecurity. All cryptography is really about maximizing entropy. And all the present algorithms, even those which are called post-quantum cryptography, they, for whatever reason, they choose to use mathematical functions, sometimes very complicated, to add entropy to the message. In Randemon, we took completely different approach. Because we had a very good random number generator, we thought about not adding this entropy to the message, but adding message to the stream of random bits, which is, there is no such a type of ciphers up to now. This was patented. We got patent number 12 million something. The method is very simple because it does require a very simple insertion. It can be programmed on a stack with just few steps. So it requires very low computing power, unlike all the classical and post-quantum cryptography, which usually, especially for longer keys, it requires enormous amount of computing. On the other hand, even short key creates a huge number of permutations, and the longer key doesn't require more computing power. So the Barn cipher, Barn means bury among random numbers, but it also has connotation of the haystack. When it's hard to find the needle in the haystack. It works very simply. If you have a stream of bits, you have your message, and everything in the digital world is really a set of bits. You can insert those bits in some places defined by your key. Here I choose a very simple short key of the 4 digits or 4 numbers, but it can be much longer. And of course, I marked my inserted bits in bold, but in reality, they are the same as the other bits. So that's why cracking this cipher is so complicated. And of course, one can try to do brute force analysis But even on such a short cipher, one can see there are many solutions. And on the practical side, it's very hard to find which solution is the real one. Even using quantum computer, we did some estimate that for the octal 512-bit key, it will take 10 to 20 lengths of the word. The word has about 10 to 13 years, whereas this will be many, many times longer and one even doesn't know how the quantum computer will compare these solutions. So that's why this is a very efficient kind of a cipher. On the left, I showed you why beta decay converted to light through the electroluminescence is random. You can see that the light emitted by those so-called trigger lights, those are used in the watches to illuminate the numbers. They are very random because the electrons are hitting different times and different places. On the right, I showed a typical text, which obviously has a very low entropy, and you can see it. It's there are plenty of zeros because in the encoding, if we use 16-bit Unicode, there are mostly zeros. The standard 24 letters are very few, and so the text is not really very random, but after running through Barn, you get something which is very, high entropy.
Random, yeah.
Visually random, as those pictures which 41 years ago you published, and I never thought that the same method can be used for testing. So, to finish my short presentation, and again to thank you for changing forever my life, I'd like you to remember that good random numbers are produced. They are not generated by any algorithms.
But what are, say, two acceptable methods of doing that?
Not really. I mean, physical. The best way is to have a physical. Physical noise, but it has to be quantum. I will talk in a moment about that. AI, which is basically a database, and if you have enough data, you can find, looking at the sequence, you can find what was the formula to create that sequence. So that's why these arithmetic methods are not good, because databases are growing, and now people can basically compare the sequence and say, okay, well, this is this formula. As I mentioned before, only physical quantum sources are really good because they are independent on our daily life. Most noise is dependent on temperature, electric field, magnetic field, gravitational field. Even those quantum sources, they have to be tested. There is a Bundessicherheitsinstitut, which it's equivalent to NIST in US, which issued the long description what physical random number generation should do, and they say that they should provide some kind of a distribution. For example, Poisson distribution of times between decays, or Gaussian distributions if we are talking about space distribution of events. And last but not least, when you are running any simulations, Monte Carlo simulation, using random number generator, don't trust programmable or pseudo random number generators, because they usually have much too short sequences, and the life nowadays is so fast that you can easily overgenerate and use the sequence many times. So I'd like to thank everybody, and especially you, Richard, because you really changed my life. I think it's obvious. Thank you.
If you don't mind, I got one question for you.
Yes.
Did you ever do any of your research applied to steganography?
Yes.
That's fine.
That's what we call our cipher. It's a steganographic cryptography.
Okay.
Classical steganography is to hide in some image or something, but usually you are not hiding in the random noise. So that's the big difference. And of course we do have some trade secrets how to make.
Yes.
No, well, we can discuss privately.
Thank you.
There are many, small things which make the cipher really hard to break.
Yes.
By the way, on our webpage, randomon.com, I am now offering $5,000 for everybody to break this cipher. There is a binary file, and you can try. For the last year, nobody could. So.
Thank you.
So your point is it's worth more than 5,000 to you to have the answer?
Yes, I was contacting, there is an Australian expert, the guy who broke so-called Zodiac cipher, if you know about the guy's infamous Zodiac thing. And this guy said that his fee for trying to break will be 100,000. We are just applying for the European Union grant, and if we get the grant, we budgeted 100,000 for the expert to try to break. There is no, mathematically you cannot prove that the cipher is good or bad. This stems from the Turing theorem, basically.
Did you mention what are they called? Something pad.
One-time pad, yes, one-time
That's
pad.
unbreakable.
That's unbreakable, that Shannon proved it, but it has the big problem. You have to deliver every time the pad.
When I was in the military, that's what I used all the time.
Well, on the red phone line used between White House and Kremlin, they used one-time pad.
Oh, you're kidding.
Yes, but because they had the guy who was basically having,
He carried
carry over there
Right.
the book.
That was secure.
This is the only way. Nowadays we have a different method, which is called quantum key distribution. By using entangled photons, you can send any key, and you know if somebody is eavesdropping. But unfortunately, the systems are very slow. They have few kilobytes per second, so it's not very practical yet.
Yeah, I don't want to sound ignorant here, but suppose Alice is sending Bob a message using Barn. They don't each have to have access to the same random bit stream, do they?
No, for the decryption, you don't need.
Okay.
This is the advantage of Barn. Only to encrypt, you need the stream of random bits. You are talking about so-called stream ciphers, when people are generating using PRNG. But in this case, it's only needed on the encryption side.
Okay.
The Alice needs a
That
key.
must be the case, but
Yeah. Well, I have a Macintosh application. If you like to test and use it, I can give it to you. It works very efficiently because it creates a fairly compact code, and you can encrypt anything, images, text, whatever kind of a file. I'm sorry, it's a little bit longer,
Not a little. Oh, go ahead. Thank you.
but we started later.